So I'm going to spend some time today talking about a data streaming platform that we built on top of Kafka. So we're not going to see any code in this presentation, and you're not going to learn anything in terms of tricks on how to optimize Kafka. We've seen a lot of that at this conference so far. What we are going to see is, first, we'll talk about why we needed to build this platform, and then I'll take you through the various characteristics of the platform, how it leverages Kafka, and how it achieves its goal. So let me begin with why we actually built it. And hopefully, some of these things will help you to understand why we didn't find anything kind of out there already. No available prior art that actually fit all of the pieces in the way that we needed them to. So the first thing we needed is the ability to co-locate our stream processors as close as possible to both the data and the logic around that data. And so we did not want to be in a situation where we were running in another piece of infrastructure somewhere and then making calls over the network to try to induce some other system to get work done. We wanted to be right there inside of these hosts. That's where all our business logic lives, and that's where access to the data is readily available. The second piece of this is that we need data isolation. The reason we need it is that many of our use cases are moving our customers' data from instance to instance of our products in the cloud. It could be within a region in the cloud, could be cross-region. And we don't want to mix the data that's moving through these pipelines with data from any other customer. So we need that data isolation, very important. We do a lot of data migration, and one of the things about data migration is that data that may be ill-prepared or ill-formed for the target system may have been perfectly fine in the source. I think even in the some of the prior presentations, there was much talk about transformation. What we wanted to be able to do is catch these errors, these invalid data records in flight while they're moving, and be able to alter the characteristics of the pipeline without having to start over again. And the fourth major piece of this is that we do this a lot for many, many customers. We have a very large number of customers, and many of our use cases that the customers leverage happen very often. And so there isn't really enough capacity out there to do all of these at once, and we certainly don't want to over-provision our product and system services. So we have a very strong need for being very efficient in the way we use shared resources. And those resources are both things like the Kafka clusters, and they're also our product instances, our product services, which are also shared across tenants in most cases. So at its core, this should look familiar to everybody. It's ETL, right? It's streaming ETL. And there's lots of systems out there that can do streaming ETL, but not with the characteristics that I described. There are a couple of other characteristics as well that I'll touch on as we go. But the starting point for thinking about how this platform works is streaming ETL. Now, one of the things about the way these pipelines are laid out is that the various kinds of stream processors involved can live in lots of different services in our ecosystem, all participating in a single data movement pipeline. So the source may live in one host, one type of host, transforms somewhere else, syncs somewhere else. Communication between those things are dedicated Kafka topics. So that's what we're seeing in this diagram. Just very simply, source to a topic, to a transform, to another topic, and to the sync. And we follow something that you might call bring your own host. As I said, we don't have specific infrastructure services that host these stream processors. They live in our service hosts. So they use libraries and SDKs that the Lithium platform provides to many teams throughout the company. And they get integrated into their own hosts. So this is just showing an example that source, transform, sync, they live in separate physical hosts. These hosts are heterogeneous. So it could be product service, hosting maybe a source. Transform may live in some kind of infrastructural service that is doing some kind of manipulation of the data based on other data that it has direct access to. And the sync in yet another instance of a service. So a quick example of this might be that we're moving data for a customer from a Jira instance that they have in the cloud to a different Jira instance that they have somewhere else in the cloud due to maybe consolidation within their organization, acquisitions. These things happen all the time. And as I said, these pipelines are all isolated. So that means that even though there may be pipelines being hosted or pieces of pipelines being hosted by the same instance of a service, they will internally be kept separate. So that means separate instance of the source, separate topics as the data moves downstream all the way end to end. So how do we actually define what these pipelines look like? We do it in something called a work plan. The work plan is essentially declarative. It's a spec. It specifies the kind of source that will be used. For example, the sync, the transformers. When I say transformer, I actually mean more than just transformations, but I also mean validations. So I may just call them transformers from here on in, but I'm talking about both of those things. So these are all specified in this work plan spec. Information about parallelism, which is both how many partitions will be provisioned in these topics that are being set up, as well as some information about the number of workers that we want to see provisioned within our ecosystem to support the data movement. And then there's a number of other things involved as well. There's runtime context, which is some specific information that'll be collected when this whole thing is set up by our orchestration system that gets passed down to all of these processors so that they have some understanding of the context that they're working in. Just a quick example of what I mean by context. what customer is this, or what tenant is this? And that's going to be important a little bit later in this discussion when we talk about how resources are actually chosen to participate in a running work plan. We also have a concept of data sidelining, which has to do with remediation. So I'll talk quickly about it here. The platform is set up such that you can run into invalid data in the validation function. You can move that data off to the side, and you can let the rest of the data continue to move. Right? And we call that data sidelining, and that is what's used when we get to remediation, which I'll talk about later. Another piece of this that's worth mentioning is that sources, transforms, validators, sinks are all stateless. And they're stateless because the Lithium Platform team is controlling that, and that's an architectural principle that these processors will not maintain their own state. However, there are a lot of good uses for state in a data pipeline. And so there is another kind of processor that can be optionally configured in the work plan that can take events from these other processors and render state from that. We'll see a diagram of this later, and you'll see how we're doing that. So in order to make all of this happen, we have a fairly sophisticated control plane. The control plane is responsible for things like work plan management. There can be many, many work plans that are either waiting for execution or actively executing with pipelines running in the system at one time. All of that is understood and managed in a stateful way by control plane in the work plan management piece. There's also what's called resource provider management. So a resource is the integrated components that live inside of data plane services. They don't know about each other, but control plane knows about all of them and is coordinating certain things with them all the time. They're in constant communication through heart beating, et cetera. And then there's topic management. So I mentioned a little bit earlier that when we spin up a pipeline, we actually spin up topics that are used specifically for that pipeline. And we tear them down when they're done. And so that is managed by control plane as well in topic management. There's a fairly simple architecture for communication between control plane and data plane. It is, again, based on Kafka. These are events that flow one topic for each direction here, control plane to data plane, and the other way around on a different topic. On one side of it, you can actually think of it as a message bus. Right? So when control plane emits events, and I'll talk about these events soon, all of the data plane resource provider instances get the message. Okay, so that's not a partitioned workload, that's a pure message bus. Everyone needs to get the message. We're going to dig much more into how the data plane works and how things actually happen shortly. I just want to mention that along with the control plane, we have a fairly sophisticated orchestration system that sets up work plans on behalf of, we call them use cases within Atlassian, so things like cloud-to-cloud migrations or on-prem to cloud migrations, et cetera. I'm referring to those things as use cases. They work through the orchestrator, but there are many other steps involved in making that kind of data movement happen. The Lithium orchestrator is tightly integrated with Lithium and also integrates with other components within our ecosystem. We have a REST proxy for those in the company, and there are many, who are not prepared yet to move to a fully event-driven system, and currently are familiar with REST. We do provide a REST proxy for communication with the control plane. That REST proxy actually uses the event topics to communicate with control plane. And then we have the ability for other things that also want to pretend to be orchestration engines, command line tools, et cetera, that again also work using the same mechanisms, either through REST or directly through Kafka topics. Wow, this is just a diagram with a lot of lines and stuff on it. So this is just a little more information about the pieces within the control plane and how they communicate. I think an important piece of information here is how control plane does its own state management. So all of the mechanisms that I talked about within control plane are based on Kafka Streams. Workplan management is actually nothing more than a Kafka Streams aggregator. It's taking all of these event messages that are coming in, and it's manipulating state for each of the work plans that are in flight or preparing to be in flight. That is done using exactly one semantics in Kafka Streams, which means that it's completely reliable. If we lose the instance of the control plane that happens to be managing that work plan, that will reliably be picked up by another instance of the control plane. And our other management pieces inside of control plane all use the same technique. And so all reliable through state. That state managed in Kafka, in change logs, for anyone who might know what goes on under the covers in Kafka Streams. That is the source of truth. So the source of truth for work plan management are those topics, compacted topics. Okay, so let's dig a little bit deeper into the anatomy of a data plane resource provider. So that resource provider might be a provider for sources or sinks or whatever it might be. Inside of a host is an integrated component from the Lithium SDK. That is the resource provider. It's the thing that is communicating with control plane. So heart beating, other messages, which we'll get to shortly, everything communicates through the single resource provider that's integrated. Its job is to make some decisions about spinning up resources on behalf of the work plans and creating them also inside the host. So in this diagram, you see a resource provider communicating with the control plane topics on the left, and it's actually provisioning instances of processors within its control inside the host. For anyone that's interested, I think, yes, I did mention it here, but we actually use an actor model. So we've taken the asynchronous messaging mechanisms and patterns that we use with Kafka at the larger scale, and we're doing the same thing inside the host. So all communication between resource provider and the processors that it's responsible for is through an actor model. And then those individual processors can communicate with data plane topics, and that's what you see here in pink. This is pretty similar for all of the different resource provider types, sources, sinks, et cetera. There's one that's a little bit different that I will talk about a little bit later. Now, we have a lot of services running at Atlassian, and because of that, there can be many, many instances of those services that might be candidates for participation in a work plan or might not. And that decision is left to the instance itself. So control plane doesn't get involved in understanding whether a processor should be provisioned in any given instance of some service that's out there. It's actually up to those instances to kind of raise their hand when they're asked to, and let control plane know it's available for participation. What we do is we use an auctioning model in order to make this happen. When a work plan is prepared to be executed, the work plan will be put up for auction. So a message simply goes out on the control plane event topic and says, this work plan is in this state. It would be the auctioning state in that case. Here's all the information that we talked about earlier in the work plan spec. And now it's up to each and every one of these instances that are out there in the data plane to either bid or no bid on participation on this work plan. There are many reasons why an instance may choose to bid or not bid. It could have to do with how much capacity is available in that instance at any given time. It could be whether it's the right kind of instance to support that work plan. It might be due to the context information that I was talking about earlier, like the tenant ID. There's no point in a service, let's say that's supporting Jira, in saying I can participate in this work plan if the tenant whose data is being moved in that work plan is not being serviced by the shard that service instance belongs to. So there are many, many criteria that are used with all local reasoning to determine whether it should be a bid or a no bid. So let's talk about what happens when it is a bid. And in this example here, I'm just showing a bunch of hosts, some of which understand the sources, some understand the transformers, some understand sinks. This may not be so obvious looking at the diagram, but on the left, what I'm showing is those instances that actually bid, so they're interested. And I tried to make the highlighting on those a little bit darker, hard to do with Excalidraw. If anyone is out there who works on Excalidraw, you need a thicker line. So all the bids will come in, and then the auction window will end. Right? So in our case, we use somewhere between a 5 and a 10-second auction window. And we now have to take all of those bids within work plan management and control plane and make decisions about who should win. Right? And we try to spread the work around based on capacity, based on noisy neighbor, tenant information, et cetera. And we call that auction reconciliation. So that's the first step. Work plan goes out. bids come in, auction closes, winners are selected. After those winners are selected, the next step is to provision topics, because you cannot spin up components that register with Kafka topics as consumers if the topic doesn't exist yet, right? So the logical next step is to provision topics. Topic management within control plane communicates with the Kafka cluster, provisions topics. The next phase is then resource provisioning. So as this work plan state changes, it will change to a provisioning state. Again, all of the data plane components will get the same message to show that this work plan can be provisioned. They'll look to see whether they're in the list, whether they should provision or not, and those that are, I'll say will attempt. Of course, they don't have to be able to provision, but they will attempt to provision. So this is what we're seeing here. Some of these winners here are now showing resources having been provisioned within their own process space. This is now a work plan ready for execution. And here's another view of what that looks like. So in our work plan, we had said that we only needed one source. So the data is being pulled from some data source somewhere. It's being passed into the input topic. We actually provisioned 2 transformer workers, so they're sharing the load here through standard Kafka consumer group balancing, all writing to the output topic. And then we were able to get 4 workers involved. So that's what we're seeing here. I said that there was a processor that doesn't quite follow the model that I showed earlier. There's a little bit more going on inside of the source. There's an extra topic and an extra process that happens inside the source. Data is actually collected through a collector piece and written into an ingress topic first. And then there's an usher that pulls data from the ingress and into the input topic. Why? Seems like maybe an unnecessary extra step. The reason here is that the platform supports pause, resume, remediation, and rewind. Right? And specifically with rewind, it can be very expensive for us to go back and collect the data all over again from the data source. The work has been done. We cannot do rewind as maybe those of you who would reset your Kafka offsets as a rewind. We can't do that because we use Kafka Streams extensively throughout the process. And this is probably not the right talk to talk about why rewind with Kafka Streams it's not impossible, but it's near impossible to get right. And so what we do is we build this ingress topic. And when we get to a rewind phase, what actually happens is the source will itself reset, go back to the beginning of the ingress, and start pushing the data into the input topic all over again with a different generation number. And everyone knows about the generation number. They'll skip data that's in an old generation when the pipeline starts up again. And we also truncate data through the Kafka admin client when we do a rewind like that. So a little bit different, but from the view we saw earlier, it still looks the same. Now, we can have multiple transform processor chains operating one after the other. So what do I mean by that? There can be many, many transformations in a pipeline. And what we do is we wire them up as one thing within a resource provider. And we treat it as one large transformation. They're written separately. The teams that write them are not necessarily the same teams, but they're wired up by the Lithium client code to act as one thing as it pulls data from the input and then ultimately sends the data to another topic. And what I'm showing here is that these two can have multiple workers. So I'm just showing 2 workers for the transformations in pink. They're going to an intermediate topic. So if multiple transform chains were set up in the work plan, there'll be yet another topic set up in between those steps. And so that's what's being shown here. Input to transforms, to an intermediate topic, to another chain of transforms, and then to the output topic. We also can have multiple sync processors, but in this case, they're not serialized, they're parallel. And an example of that, of why we have that, might be that we might have, let's say, product services that are interested in taking the data and putting it into their own product stores. But at the same time, we may have other data analytics or other systems that also want to consume that data at the same time and do different things with it. So the work plans support many different sync processors at the same time. And of course, they would be syncing theoretically to different data sources. This is a view of kind of the internals of the state processing that I was talking about. Each work plan can have a single work plan state processor that can have many functions in it. They're all feeding all of the other processors are feeding events onto a single topic that is also set up purely for that work plan. And then it's being processed by these custom state processors that render state and eventually feed that state back to the control plane to be merged in with the work plan state. That uses the same Kafka Streams approach that we used inside of control plane, right? It's based on aggregators. Okay, now how do we get code into the pipeline? So what I'm showing here is everything I've shown up to this point, let's put it this way, is actually operational in production, and it's running most of our data portability use cases right now. But we are in the midst of moving towards a new mechanism for actually writing the stream processing functions for how you write a source function or a sync function or a transformer. The way we do it today is pretty straightforward. You write something, you write code that gets integrated into the build of the host that that code is going to run on. Right? And what this does is that it couples the delivery lifecycle of these functions to the host's delivery and deployment lifecycle. And that's not great, because these things evolve on very different timelines. There are also a number of other reasons that I'm not going to have a chance to talk about today, why we do this, but we are basically using a dynamic class loading mechanism to deliver code that has already been vetted through another system that we're building at Atlassian to ensure that the code is safe and conforms to all of the guidelines necessary to run inside of Lithium and the hosts that host Lithium data plane. And this is done through a number of steps. We transpile custom DSL language into pure Java. We then compile that pure Java into bytecode, along with a bunch of metadata about the schema for the messages that it deals with, et cetera. And we make it available at runtime. So when I talk about a stream processing function, let's say like a particular transform function, with this mechanism, it's no longer built directly into the code base of that host. Instead, it can be pulled from our code catalog at runtime on demand and be loaded into the running system and then used as part of the execution of the pipeline. So this is a system that's currently under development. And it would require, another hour or so, I think, to talk about the details. So I'm going to leave it at that. And I'm going to leave the whole presentation right there. All right. Thank you, and you, and you, and you for being here.